So we have the strap that we've demonstrated here. And I stretched out a rubber band to pull the strap in this direction, released it, and the thing actually rotated, right? Stretch out the rubber band in this direction. Well, I couldn't quite do that, but I think when I stretched it out in this direction, we saw it didn't rotate nearly as fast, right? That was partly because the rubber band didn't really let loose down here, but I think you can pretty well understand that if the force is in this direction, there's less of it in this direction. And of course, we can break that down using, just finding the vector components, okay? And then when I did it in this direction, well, I couldn't actually do it in this direction, but I poked on it in that direction. You saw that there's no rotation, right? And that's pretty much what you would expect, okay? So that's a direct experience, and you're welcome to go over there and push it this way and push it this way and poke it that way, okay? Probably ought to do that and convince yourself that it really behaves the way I say it does, because then everything will mean more to you. Okay, so question is, if this thing is released, if the force is applied through some distance, and even though with the rubber band it's a variable force, you still have an average force, and so I'm just assuming a constant force here, and we're not really losing anything by doing that, but you can convince yourself of that. Okay, so if the force is applied through a small angle d phi of rotation, okay, and the force is exerted at distance r from the axis, the question is how much work is done by each, right? Okay? Now actually, the answer I got was what'd you say? F dot what?
R d phi.
R d phi isn't a vector.
I don't see why not.
Huh? Oh, wait a minute. The vector R, d phi. Is that right? Okay. So, good idea. Actually, not quite, but you'll see why. But still, good notation, good thought. Okay, now, well, first of all, and that's d phi, not d theta. The force is exerted through a displacement that's equal to this, right? Now, if we want the vector displacement, when it's in this configuration, if the eye is in the direction of the beam, then the displacement is in the j direction. Now, as it rotates, the displacement changes direction, right? But we have a very small angle of rotation, so there's no significant change in the direction, so we just say it's in the j direction. For an infinitesimal phi, that's going to be the case, right? Okay? So, I would think that you would maybe want to modify this and say it's work done is F dot delta. And I've got a D here and a delta here. I'm going to call it a ds, okay? F dot ds. Okay? And that would be let me just factor the constants out. You got an R I'll do it this way. And I have reasons for separating the R and the D phi, but I could put an R D phi over here, and it would actually make more sense, and I probably should have, okay? But you understand, that's going to be the expression. And if you don't understand dot product well enough to do that, go back to chapter 1 of your textbook and learn it. And do that. Along with cross products, all of which are things that you theoretically should have seen, at least the dot product in pre-calculus. Okay? And we talked about the cross product briefly early in the semester. So make sure you understand both of those as best you can, because we're going to be using them very soon. Okay? Okay, well, back to the problem then. ds is this. So in the first case, your force is in the direction of this, right? Okay. First case being, let's say, this one, second case, third case. And I'm using green here, and I'll write this in green. So it should be so you should have just FR d phi, right? Because it goes distance R d phi in the direction of the force, right? So it'll just be the product of the force with the ds, displacement. So I didn't use the vector notation here. We'll reconcile this with the vector notation in a minute. In the second case, which is orange, so we'll call this 2. Okay? Only the component of the force parallel to the displacement counts. Only the force parallel to the displacement does work. So that F sine theta is in the J direction. Okay? Okay. Now I'm using deltas on one side and d's on the other. I'm going to change my deltas to d's. Okay. And then in the third case, F is in the I direction. So the work done is 0. Okay? Because remember that the work done is equal to the perpendicular component of the force multiplied, or the parallel component of the force multiplied by the displacement. Okay? So the only component parallel to the force here is the F sine theta. The only component of the force here parallel to this displacement, well, is 0. But all this force is parallel to the displacement. Okay? Now this is key. This is not something you look at and forget when you see a formula. Okay? This is the reason for the formula. So what's the formula?